Hello, welcome to Basics of Finite Element Analysis Part 2. This is the last week of this course, and today we will continue our discussion for plane elasticity problem. What we did in the last problem was that we developed the weak form for two equations of motion associated with the problem, and these are the two equations which we have developed. The next step in this sequence is that we have to approximate these u's and v's, right. So, we have to approximate them in terms of approximation functions. So, now we know that u for any element, this is a dynamic problem. So, it depends on x, it depends on y, and it also depends on time. So, the way we do this approximation is that we say that the approximation in the space, we use our approximation functions, and the values of u's at nodes, they themselves are functions of time. So, in this way we separate the variables. The nodal values are functions of time, and the spatial variation does not depend on time. This is what we do. And this is exactly the same thought process which we adopted for one dimensional dynamic problems when we did, which we did in the earlier course. So, the approximation for this is j equals 1 to n uj, and uj is a function of time, but it does not vary in space, it is specific to a node, and then psi j x y. Similarly, v for the eth element, which depends on x, y and t, equals summation over 1 to n Vj, which is a nodal degree of freedom for the eth element, times psi e, which is a function of x and y. So, we can use these relations in all these terms ux, vy, uy, vx, u double dot, all these terms. The other thing is we have to make a choice for weight functions. So, I say that W1 is a function of x and y, and it is same as psi I x and y, okay. And the second weight function is also psi I x and y. So, once we do this, so let us call these equations A and let us call this B. So, this is, excuse me, this is W2. So, we put B in A, and what we get is, so we will do this for the first equation. So, the first equation looks like this. So, I am integrating over the element He that we have plugged, we are going to plug equation B into A, and we are also clubbing equations with same coefficients. So, for u the coefficient is uj and for v the coefficient is vj. So, we are clubbing this term and this term together. Okay. Similarly, we will club Vy term and Vx term together. So, that is how we will be able to club them together. So, C11 Ux corresponds to C11 Ux is del psi I over del psi j over del x, and that is multiplied by W1, which is del psi I over del x. Okay. Plus the other term is coming from C66. So, C66, and this is multiplied by del W1 over del y. So, I get del psi I over del y, and I am getting uy. So, I get del psi j over del y, and this entire thing is multiplied by uj, and uj is a function of time. Uj is a function, I am not putting it here, but it is a function of time. So, this takes up care of green terms. Okay. So, this term, the second derivative, I will keep it separate. I will keep this term separate. We will see it why. Then, so I have collected all the terms which are underlined in green. Next, I will collect all the terms underlined in red. So, I get plus summation j is equal to 1 to n. So, first is del W1 del x times C12 times Vy. So, del W1 del x, it gives me C12 del psi I over del x times Vy, and V is Vj times psi j. So, I get del psi j over del y, because V is being differentiated with respect to y. Okay. Plus I get a term from C6. From C66 here I have del W1 del y. So, I get del psi I del y, and I have Vx. So, I get del psi j del x. Okay. So, this is the second block of terms, and then I get a third term related to this inertial term. So, here I get, oh, there is this has to be, I am sorry, I should have multiplied this by, see in this earlier equation the entire expression is being multiplied by W1. So, we missed writing W1 here, and we also missed writing W1 here in the second equation, W2. Okay. So, there was an error there. So, the inertial term I get it as, actually it is summation j equal 1 to n rho, from W1 I get psi I, from u double dot I get psi j, but it is being differentiated with respect to time twice. So, which term will get differentiated? Cj, this Vj, no, sorry, Uj will get differentiated twice, right. So, it will be Uj double dot. okay, uj double dot, and this entire thing is integrated over the domain d omega. I still have not taken care of w1 fx and this boundary term. So, I will move my w1 fx on the right side, integral over the domain he, w1 fx becomes psi I fx d omega plus, okay. So, sorry, so because now I am shifting it to the other side, I will remove this 0 and he, so the other term becomes integral over the boundary of w1 gets replaced by psi I times Tx times ds, okay. So, we have to be a little careful because there are lots of terms and we have to keep our, we have to do the book keeping correctly. Now, this term involves uj, this is multiplied by uj, this entire integral. This entire integral of this entire term is multiplied by uj. When I integrate this over the domain, uj does not play a role because uj is purely a function of time. So, it does not matter what uj is. When I am doing this integration, it is this thing which matters. So, this term is multiplied by uj, this term is multiplied by vj. So, I missed out vj here, okay. Where does vj come from? See, these are all red terms. So, in red terms you have v, vx and vy. So, this term involves is multiplied by vj, and the third term is this, it involves the second derivative of uj. So, I can call this green term as k11 ij. I can call this red term, why is it 1 Because it involves the first equation. So, the first index superscript corresponds to the first equation. The second superscript corresponds to u, which is the first primary variable. Then we call this k12. Why is ij? Why is it k12? The first superscript corresponds to the first equilibrium equation, right, which is for the x direction. This entire equation is for x direction. So, the first superscript corresponds to the x direction equilibrium, and the second superscript corresponds to the second primary variable because it is multiplied by vj. And this I call it element of another matrix because it is involving a density term. So, it is related to the mass and it is multiplied by inertial term, this acceleration u double prime. So, this is the mass related term. So, this will be what? M11, 12, 21 what? It first superscript corresponds to first equilibrium equation and it is multiplied by u, second derivative of time derivative. So, it is my mass matrix M11 ij, and this is F1 and this is Q1. Okay. So, in matrix form I can write this equation as K11 u. See, K11 is multiplied by u vector plus K12 and that is multiplied by v vector plus M11 u double dot is equal to, if I add F and Q, I can call it F1 plus Q1. What you see is that in this equation there is no M12, there is no M12, there is only M11. Similarly, for the second equation, so this is from first equation. For the second equation, I will get K21 times U, and please note this is for which element? This is not for, this matrix will change from element to element, right. So, this is for each element, but I am just ignoring this E for the time being for simplicity purposes, but all these are for each element. So, this is K22 V plus M22 times the second derivative of time derivative of V equals F2 plus Q2. So, this is the second equation. Understood? And if I do the assembly, so these are, so how many equations? The first, so this is first set of equations, this is second set of equations. How many equations do we have in the first set of equations? Suppose, so it depends on what type of element we have. Suppose I have a rectangular element which is having 4 nodes, then how many equations we have from the first set of equations? 4, right? And from the second set of equations we again get 4 equations. We have 1 equation corresponding to each node. So, for this thing, for such an element we will have 8 equations. If it was a triangle, linear triangle, then we will have total number of 6 equations. If it was a quadratic rectangle, then this has 9 nodes, this has 9 nodes. So, it will have 18 equations and so on and so forth. Okay. So, I can now club these both set of equations into one big set of equations, and that is what we will write. K11. So, this big matrix has 4 sub matrices. Okay. So, if there are n nodes, if there are n nodes in the element, then this big K matrix, what is the order? It is 2n by 2n, it is 2n by 2n. The other thing is that earlier we had said that C12 was same as C21. This is true for isotropic materials and orthotropic materials. Okay. If you do the math and you work out all the details, because of that equivalence and for these equations, K12 is same as K21 transpose. Also, when you will do the math, you will see that K11 is symmetric, and also K22 is symmetric. So, because this is symmetric and this is transpose of this, the overall K matrix is symmetric. So, if you can compute only the top half of the matrix, you do not have to compute the lower half, because all those numbers you can directly assume through notion of symmetry. Okay. So, I think this completes our discussion for today. Tomorrow we will continue this discussion further, and we will close this topic and also bring this course to a logical end. So, thank you very much and have a great day.